to my class in linear algebra. For today, we will discuss the second operation on matrices, multiplication of matrices. But before that, we start up with the scalar product or dot product of two vectors, element of the n-dimensional space Rn, or R to the n, or R sub n. Let U and V be elements of the n-dimensional space R to the n. When we say R to the n is an n-dimensional space, it consists of points with n coordinates. And the coordinates of these points in Rn are real numbers. Hence, if U is an element of the n-dimensional space R to the n, U is a point with n coordinates, 1, 2, 3, up to n coordinates. And these coordinates are elements of the set R, or they are real numbers. If n here is 1, you have simply the real line or the one-dimensional space. If n is 2, you have the Cartesian plane or the rectangular coordinate system or the two-dimensional space, where the points in R2 have each two coordinates. If n is 3, you have the three-dimensional space, and each point in the three-dimensional space, or R to the power 3, has 3 coordinates. But here U and V are elements of R to the n-dimensional space. So U and V are points with n coordinates, as indicated by the last subscript of U and V, n. And these coordinates, U1, U2 up to Un, and V1, V2, V3 up to Un, are real numbers. Now we define the scalar product or dot product of these U and V elements of Rn. They are also known as vectors. And last time we defined a matrix with only one row as a row vector. And these elements U and V of R to the n may be taken as row vector or matrices with only one row. And we also say that U and V are n tuples of real numbers, because U and V each has n coordinates. So U is an n tuple of real numbers because U has n coordinates, and these coordinates of U, U1 up to Un, are real numbers. V is also an n tuple of real numbers because V has n coordinates, and these coordinates of V are real numbers. The dot product or scalar product of the n tuples u and v elements of R to the n is denoted by this notation. You read u dot v, and u dot v is given by this sum of products. And you can see from this equation that corresponding coordinates of u and v are multiplied. u1 is multiplied by the corresponding coordinate of v1, and the second coordinate of u is multiplied by the corresponding second coordinate of v, and the third coordinate of u is multiplied by the corresponding coordinate of v sub 3 up to the last coordinate of u sub n is multiplied by the corresponding nth coordinate of v. And the products are added together to get the sum, and the sum of the products of the corresponding coordinates of the two vectors u and v, or the two n tuples of real numbers u and v, is denoted by u dot v is called the scalar or dot product of the vectors u and v, or the n tuples u and v. Now this right hand side can be written more compactly using the sigma notation. The dot product of the two vectors u and v, denoted by u dot v in compact notation, can be written as the summation of the products u sub I and v sub I for I is 1 to n. If you will expand this sigma notation for I is 1 to n, if I is 1, you get u1 multiplied by v1, which gives the first term of this sum. And summation, in the operation indicated by the sigma notation is addition, plus when I is 2, you get u2 multiplied by v2, which is the second term of this sum, plus up to plus for the last value of I, indicated by this upper index of the sigma notation n. When I is n, we get the last term of the sum u sub n times v sub n. We now take an example to get the scalar product or dot product of two n tuples. For our example, consider the following row vectors. U is a vector or is a point with 4 coordinates, 2, -1, 1, -2. And V is a vector or a point with 4 coordinates, 1, -2, 2, and -1. Therefore, we can say that u and v are vectors in the 4-dimensional space R to the 4. And we find the dot product of the vectors u and v denoted by u dot v. And the dot product of these vectors u and v are obtained by multiplying corresponding coordinates and adding the products. The first coordinate of u is multiplied by the first coordinate of v. And this product is added to the product of the second coordinates of the two vectors. -1 or -1 is multiplied by the corresponding coordinate of v minus 2. And this product is added to the product of the third coordinates of the two vectors. 1 is multiplied by the corresponding coordinate of v2, 1 multiplied by 2. And this sum is added to the last product obtained by multiplying the fourth coordinate of u by the fourth coordinate of b. Negative 2 multiplied by negative 1. We multiply 2 by 1 is 2. Negative times negative is positive, so we have plus 2 plus 1 multiplied by 2 is 2. And the last term is negative 2 multiplied by negative 1 is positive 2 plus 2. And we add the products, we get 8. Hence, the scalar product or dot product of two vectors u and b with each with 4 coordinates is 8. And 8 is a real number and 8 is a scalar. That is why this product of u and b is known as scalar product or dot product because the product is actually a scalar. In this example, the scalar is in particular a real number. Now suppose we take v dot u. To obtain the dot product of the vectors v and u, we write first the vector v, given by 1, negative 2, 2 and negative 1. And we get the dot product of v and u. We now write the vector u with coordinates 2, negative 1, 1, and negative 2. Now we multiply corresponding coordinates and we add the products. We multiply the first coordinates, 1 multiplied by 2. Plus multiply the second coordinates, negative 2 by negative 1. Plus 2 multiplied by the corresponding coordinate 1. Plus the product of the last coordinates, the fourth coordinate of b, multiplied by the corresponding fourth coordinate of u. Negative 1 multiplied by negative 2. And we perform the operation multiplication. 1 by 2 is 2. Negative 2 by negative 1 is positive 2 plus 2. 2 by 1 is 2 plus 2. And the last product is negative 1 by negative 2 is positive 2 plus 2. And we add the products, we get 8. Hence, we can see from this example that the dot product of u and b, 8 is the same or is equal to the dot product of b and u, also equal to 8. Thus, we conclude by this example that dot product or scalar product of vectors satisfies the commutative property or commutativity property . Our conclusion from this example, we thus conclude that u dot b is equal to v dot u. That means a scalar product or dot product satisfies the commutative property. And we will now prove in general that dot product of two vectors satisfy the commutative property. We now prove in general that dot product of two vectors satisfies the commutativity property. Prove u dot b equals v dot u, where u and v are elements of R to the n, or the n-dimensional space R to the n. If u and v are elements of R to the n, then each of them has n coordinates, or each is an n-tuple of real numbers. For the proof, we start with the given. We let u, v be elements of R to the n. That is, if they are elements of u to the n, u is a row vector with n coordinates, u1, u2, u3 up to un, and these coordinates u1, u2, u3 up to un are real numbers because u is in the n-dimensional space R to the n. Similarly, v is an element of R to the n, thus v is a vector, a row vector in particular with n coordinates v1, v2, v3 up to vn. And these coordinates of v, v1, v2, v3 up to vn are real numbers because v is an element of R to the n, or the n-dimensional space. Then we start from the left-hand side, we obtain the dot product of u and v. And instead of writing all the terms in the sum of the dot product of u and v, we use the compact notation, or we use the sigma notation to write the dot product of u and v. And the dot product of u and v using sigma notation is given by the summation of u sub I multiplied by v sub I, or we may omit the dot here. U sub I, summation of the product u sub I and v sub I, and from your algebra we know that this is the juxtaposition notation. There is no operation or symbol indicating the operation multiplication between u sub I and v sub I, but if they are side by side like this, it's understood that the operation involved is multiplication. And we call this notation juxtaposition notation, where the subscript I is 1 to n because u and v are vectors with n coordinates, 1, 2, 3, up to n. Now I said earlier that the coordinates of u and v, this u1, u2 up to un, and v1, v2 up to v sub n are real numbers. And we know from algebra that one of the properties of the set of real numbers under the binary operation addition is commutative property. That is, addition of real numbers satisfies the commutative property. That is, in adding real numbers, order of the real numbers is not important. But here, the appropriate property that applies for that product is commutative property of the set of real numbers under multiplication. This property says that if you, in multiplying two real numbers, the order is also not important. That is, multiplication of two real numbers satisfies the commutative property. Hence, by commutative property of the set of real numbers under the binary operation multiplication, as applied to u sub I times v sub I, this would be equal to the product v sub I times u sub I. So I now specify that u sub I, v sub I for I is 1 to n. These are the coordinates of the row vectors u and v. U sub I and v sub I are elements of R, the set of real numbers. So these numbers u sub I and v sub I for I is 1 to n are all real numbers. And we apply the commutative property of multiplication of real numbers. And that property says that in multiplying two real numbers, order is not important. Thus, if order is not important, the product u sub I times v sub I is equal to or the same as the product v sub I times u sub I. And that's the commutative property of multiplication of real numbers, in which order is not important in multiplying real numbers. But consider now this summation of the product v sub I times u sub I. This is exactly the dot product of the vectors v and u. The summation of the products v sub I, u sub I for I is 1 to n is by definition of scalar multiplication, scalar product or dot product of two vectors. The summation of v sub I times u sub I for I is 1 to n is the scalar product or dot product of the vectors v and u, denoted by v dot u. And that completes the proof for the commutative property of dot product or scalar product of two vectors. And the end of proof is indicated by this shaded circle. Shaded rectangle. For your practice, try to prove that that product or scalar product of n tuples or vectors in Rn or n-dimensional space also satisfies the associative property. That is, you prove that that quantity v dot w is equal or is the same as quantity u dot v dot w. And for the proof, you let u, v, w be elements of R to the n. And because u, v, w are elements of R to the n, the coordinates of u, v, w are real numbers. And we know that from algebra, the multiplication of real numbers also satisfies the associative property. That is, in multiplying real numbers, grouping is not important. We now define the product of two matrices. Now, the product of any two matrices may or may not be defined. That means that the product of two matrices may be defined, or the product of two matrices may not be defined. That means we cannot multiply just any two matrices. There is a condition that must be satisfied by the two matrices so that their product is defined. Let A be an m by n matrix. This means that matrix A has m rows and n columns. And we let B be an n by p matrix. This means that B has n rows and p columns. Now you notice that A has n columns and B has n rows. That is, the number of columns of matrix A and the number of rows of matrix B are equal. And that is the condition for the product of two matrices A and B. For the product to be defined, for the product AB to be defined, the number of columns of A must be equal to the number of rows of B. And so before you multiply any two matrices, you check if the number of columns of the first matrix in the product is equal to the number of rows of the second matrix in the product. If the number of columns in the first matrix in the first matrix in the product is not equal to the number of rows in the second matrix in the product, then you say that the product of the two matrices is not defined. Again, for the product of the two matrices to be defined, the number of columns of the first matrix in the product must be equal to the number of rows of the second matrix in the product. And you say that the product of the two matrices is not defined if the number of columns of the matrix of the first matrix in the product is not equal to the number of rows of the second matrix in the product. Then, the product of matrices A and B, written A cross B, or A times B, we read A times B, matrix A times B, is an M by P matrix. This means that if we can actually multiply two matrices and actually get their product, the size or shape of the product is equal to the number of rows of the first matrix in the product and the number of columns in the product is equal to the number of columns of the matrix, the second matrix in the product. For the product A times B to be defined, the number of columns of the first matrix must be equal to the number of rows of the second matrix B. And the size of the product A times B is the number of rows of the first matrix and the number of columns of the second matrix. That is, the number of rows in the product of matrices A and B is the number of rows in the first matrix A. And the number of columns in the product of matrices A and B is equal to the number of columns of the second matrix B in the product A times B. And the entry in the ith row and jth column, which we denote by C sub ij, the entry in the ith row and jth column of the product A and B, the product of the matrices A and B, which we denote by C sub ij, is given by summation of A sub ik multiplied by B sub kj, where k is 1 to n. And this is actually, this right hand side is actually a scalar product or vector product of two and tuples. We take an example. I here is the row number, and the number of rows of the product AB is m. Therefore, I is from 1 to m. And the second subscript J indicates the column number of the entry C sub ij. And because B has P columns, the value of J will go from 1 to P, or J is less than equal to 1, less than equal to P. The first subscript I refers to the row number of the entry C sub ij, row number of the entry C sub ij in the product A times B, because the product of matrices A and B has m rows, therefore I will go from 1 to m, or we say I is less than equal to 1, but less than equal to m. Now we take a particular entry C sub 1, 1 to show that this actually represents a scalar product or a dot product. We take I equals 1 and J equals 1. We let I and J be equal to 1. If I and J are 1, then we get C sub 1, 1. This is the entry in the first row and first column of the product A times B, the product of matrices A and B. And by definition, this C sub 1, 1 entry is equal to summation of A sub 1k, I is 1, multiplied by B sub k1, because J is 1. Where k is the column number of the entry A sub ik in the matrix A. And matrix A has n columns. B sub kj is the entry in the kth row of matrix B. and matrix B has n rows. The number of columns of A is n, the number of columns of B is n. That's why the product is defined. Therefore, K will go from 1 to n. And suppose we expand this sigma notation, remembering that the operation indicated by sigma notation is addition. So this is equal to A sub 1, 1 multiplied by B 1, 1 plus A 1, 2 multiplied by B 1, 2. If K is 1, we get A 1, 1, B 1, 1. The operation indicated by sigma is addition, so we write plus. If the next value of K is 2, if K is 2, we get A 1, 2, B 2, 1. Next to 2 is 3. When K is 3, we get B 1, 3. If K is equal to 3, we get A 1, 3 multiplied by B 3, 1. Plus up to plus, the last term is obtained when K is equal to n. The upper index of the sigma notation is n. That means the last value of K is n. And when K is n, the last term is B1n multiplied by Bn1. Now we will write the sum of the products as the scalar product of two vectors. The first vector will have coordinates denoted by A and with two subscripts. And the second vector in the scalar product is a vector with whose entries or coordinates are these numbers with B with double subscript. Thus, we have written here the sum of these products as the dot product of this vector with n coordinates a11, a12, a13 up to a1n. And these coordinates or these numbers a11, a12, a13 up to a1n are actually the entries in the first row. See, all the first subscript are the same one. The first row of the matrix A. And matrix A has n columns. That is why the last subscript is A1n. First row and n column. And the second vector with entries is also an n tuple because it has n coordinates. 1, 2, 3, up to n. And these coordinates of the second vector are actually the entries in the first column of matrix B. If you notice, all the second subscripts are the same. 1, 1, 1, 1. First column and The first subscript refers to the row number. And because matrix B has n rows, the first subscript goes from 1, 2, 3, up to n. So this tells us that to get the entry C sub 1, 1 of the product of matrices A and B, this is the entry in the first row and first column. That means you multiply the entries of the first row of matrix A by the entries of the first column of matrix B. And then you add the products. Again, to get the... So in general, again, for this particular example, to get the entry C sub 1, 1, the entry in the first row and first column in the product of matrices A and B, multiply the entries in the first row of matrix A by the entries of the first column of matrix B, and add the products as we have done here. In general, to get the entry in the ith row and jth column of the product A and B, we multiply the entries of the ith row, where I is 1 to m, by the entries of the... to get the entry C sub ij, we multiply the entries of the ith row of matrix A, where I is 1 to m, by the entries of the jth column of matrix B, where j is 1 to p. And this is a particular example. C sub 1, 1 is the entry in the first row and first column of the product of matrices A and B. C sub 1, 1 is obtained when I is 1 and j is 1. Suppose I is 3 and j is 9, and we would get C sub 3, 9. This entry, C sub 3, 9, is the entry in the product of matrices A and B in the third row and ninth column of the product A times B. And this entry is obtained by multiplying the entries of the third row of matrix A, the first matrix, by the entries in the ninth column of matrix B. And adding, because we have summation, adding the products. We now take example to apply this definition of product of matrices. We now take examples for how to multiply two matrices. Consider the following. Let A be a matrix with entries in the first row 1, 0, 3. In the second row, negative 1, 2, 1. So matrix A is a 2 by 3 matrix with 2 rows and 3 columns. Matrix B is a matrix with 3 rows, 1, 2, 3, and 3 columns, 1, 2, 3. Therefore, B is a 3 by 3 matrix. Matrix C has 3 rows, 1, 2, 3, and 2 columns, 1 and 2. Therefore, C is a 3 by 2 matrix. We find the products BC, CA, AC, and BA. We start with BC. Before you even multiply the matrices B and C, you can already tell the size or shape of the product of matrices B, and C. B is a 3 by 3 matrix. C is a 3 by 2 matrix. The number of columns of B is equal to the number of rows of A. Therefore, we can multiply B and C. The product is defined. And the size of the product is 3 by 2 with 3 rows and 2 columns. Matrix B for negative 1, 2. Second row 1, 0, 3. Third row negative 2, 1, 0. And multiply by matrix C with 3, 5 in the first row. Negative 1, 1 in the second row. And 2, 0 in the last row. We already know that the size or shape of the product is 3 by 2 with 3 rows. We start with the entries of the first row. For the first row in first column, we multiply the first row for negative 1, 2 by the first column of the second matrix. Multiply 4 by 3, multiply negative 1 by negative 1, and multiply 2 by 2, and add the products. Again, for the entry in the first row and first column, multiply the first row of the first matrix for negative 1, 2, by the first column of the second matrix, 3, negative 1, 2, and add the products. 4 multiplied by 3, plus negative 1 by negative 1. Plus 2 by 2. Now, the entry in the first row and second column, the product of B and C has only 2 columns. And the entry in this first row and second column is obtained by multiplying the entries in the first row of the first matrix by the entries of the second column of the second matrix and adding the products. We have 4 multiplied by 5 plus negative 1 multiplied by 1 plus 2 multiplied by 0. 4 by 5 plus minus 1 by negative 1 plus 2 by 0. Now we get the entries of the second row, first column. The entries of the second row, first column is obtained by multiplying the second row of the first matrix by the first column of the second matrix. And we add the products. 1 multiplied by 3 plus 0 multiplied by negative 1 plus 3 multiplied by 2. The entry in the second row and first column is obtained by multiplying the entries of the second row of the first matrix by the first column of the second matrix. 1 by 3 plus 0 multiplied by negative 1 plus 3 multiplied by 2. Now, the entry in the second row and second column is obtained by multiplying the second row of the first matrix, 1, 0, 3, by the second column of the second matrix. 5, 1, 0, and add the products. 1 multiplied by 5 plus 0 multiplied by 1 plus 3 multiplied by 0. Now, we are now in the third row. First column, this entry is obtained by multiplying the third row of the first matrix with entries negative 2, 1, 0 by the first column of the second matrix and add the products. We have negative 2 by 3 plus 1 multiplied by negative 1 plus 0 multiplied by 2. And the last entry in the third row and second column is obtained by multiplying the entries of the third row of the first matrix by the second column of the second matrix and adding the products. Negative 2 by 5 plus 1 by 1 plus 0 by 0. Negative 2 multiplied by 5 plus 1 multiplied by 1 plus 0 multiplied by 0. And we perform the operations multiplication and addition. We start with the first column. 4 by 3 is 12. Negative 1 times negative 1 is 1. 12 plus 1 is 13. And plus 2 by 2 is 4. So 13 plus 4 is 17. The next entry in the first column, 1 by 3 is 0. 1 by 3 is 3. Plus 0 by negative 1 is 0. And plus 3 by 2 is 6. So we have 3 plus 0 plus 6 is 9. And the last entry in the first column, third row, first column, negative 2 by 3 is minus 6. Positive 1 by negative 1 is minus 1. And 0 by 2 is 0. Thus we have negative 6 minus 6 minus 1 plus 0 is minus 7. Entries in the second column. First row, 4 by 5 is 20. Negative 1 by 1 is negative 1. And 2 by 0 is 0. Thus we have 20 minus 1 plus 0 is 19. The next entry in the second column, 1 by 5 is 5, plus 0 by 1 is 0, plus 3 multiplied by 0 is 0. Thus we have 5 plus 0 is 5. And the last entry in the second column, negative 2 by 5 is minus 10, plus 1 by 1 is 1, plus 0 by 0 is 0. Thus, the last entry is minus 10 plus 1 plus 0 is minus 9. And this is the product of the matrices B and C. And we check the shape, the size of the product. B and C should be 3 by 2. And we have 3 rows and 2 columns. Now we find the product of matrices C and A. Matrix C is 3 by 2 matrix. Matrix A is 2 by 3 matrix. We check if the product is defined. The number of columns of C is 2, and the number of rows of matrix A is 2. Therefore, the product is defined, and the shape or size of the product, CA, is 3 by 3, or a square matrix 3 by 3. You multiply matrix matrix C, 3, 5, negative 1, 1. And 2, 0. Multiply by matrix A, 1, 0, 3. Multiply by negative 1, 2, 1. And the product is a 3 by 3 matrix. We start by finding the entries of the first row. The entry here, first row, first column, is obtained by multiplying the entries of the first row and first column of the second matrix. The next entry, first row, second column, is obtained by multiplying the first row of the first matrix by the second column of the second matrix. And the last entry in the first row, third column, is obtained by multiplying the first row, entries of the first row of the first matrix by the third column of the second matrix. So it's like distributing the entries of the first row by each of the columns of the second matrix. We have 3 multiplied by 3 multiplied by 1 plus 5 multiplied by 1, by negative 1. Next, we multiply the first row by the second column. 3 multiplied by 0 plus 5 multiplied by 2. And the last entry in the first row is obtained by multiplying the first row by the last column of the second matrix. We have 3 by 3 plus 5 multiplied by 1. Now we get the entries of the second row by multiplying the entries of the second row of the first matrix by each column of the second matrix. Again, multiply the entries of the second row of the first matrix by each column of the second matrix. We get negative 1 multiplied by 1 plus 1 multiplied by negative 1. Next, we multiply the second row by the second column, negative 1 by 0 plus 1 multiplied by 2. And the last entry in the second row, third column, multiply the second row by the third column of the second matrix. Negative 1 by 3 plus 1 multiplied by 1. Now we obtain the entries of the third row and last row of the product by multiplying the third row of the first matrix by each of the columns of the second matrix. We start by multiplying the third row of the first matrix by the first column of the second matrix. We have 2 multiplied by 0 plus 0 multiplied by negative 1. Now we multiply the third row by the second column. 2 by 0 plus 0 by 2. And the last entry in the third row and third column is obtained by multiplying the third row of the first matrix by the third column of the second matrix. We have 2 multiplied by 3 plus 0 multiplied by 1. We perform the operations multiplication and addition to simplify the entries. 3 by 1 is 3. 5 by negative 1 is minus 5. We have 3 minus 5 is negative 2. Next, negative 1 by positive 1 is negative 1. Plus 1 positive multiplied by negative 1 is negative 1. We have negative 1 minus negative 1 minus 1 minus 1 minus 1 is minus 2. And the last entry in the first column, 2 by 1 is 2 plus 0 multiplied by negative 1 is 0, or 2 plus 0 is 2. Entries of the second column, 3 by 0 is 0 plus 5 by 2 is 10, or 0 plus 10 is 10. Next entry in the second column, negative 1 multiplied by 0 is 0, plus 1 multiplied by 2 is 2, or 0 plus 2 is 2. And the last entry in the second column, 2 by 0 is 0, plus 0 multiplied by 2 is 0, or 0 plus 0 is 0. Entries of the last column, 3 multiplied by 3 is 9, plus 5 multiplied by 1 is 5, or 9 plus 5 is 14. The next entry in the last column, negative 1 multiplied by 3 is negative 3, plus 1 multiplied by 1 is 1, or negative 3 plus 1 is negative 2. And the last entry, we have 2 multiplied by 3 is 6, plus 0 multiplied by 1 is 0, or 6 plus 0 is 6. And the shape of the product of matrices C and A, we said earlier, is 3 by 3. And this is a 3 by 3 matrix. Now, we find the products AC and BA. We now find the product of matrices A and C. First, we check if the product is defined. Matrix A is a 2 by 3 matrix, and matrix C is a 3 by 2 matrix. And the number of columns of A is the same as the number of rows of C. Therefore, the product of matrices A and C is defined. And the size of the product is 2 by 2. Multiply A is the matrix with these entries. Second row, negative 1 to 1. Multiply by matrix C with these entries. First column, 3, negative 1, 2. Second column, 5, 1, 0. And the shape of the product is 2 by 2. A square matrix, 2 by 2. We start with the first row. The entries of the product AC in the first row are obtained by multiplying the entries of the first row of A by the entries of each column of matrix C. We start by multiplying the entries of the first row of A by the first column of matrix C. We have 1 multiplied by 3 plus 0 multiplied by negative 1 plus 3 multiplied by 2. The next entry in the first row, multiply the first row of matrix A by the second column of matrix C. 1 multiplied by 5 plus 0 multiplied by 1 plus 3 multiplied by 0. Now we get the entries of the second row of the product by multiplying the entries of the second row of matrix A by each column of matrix C. Multiply the first row of matrix A, multiply the second row of matrix A by the first column of matrix C. Negative 1 by 3 plus 2 by negative 1 plus 1 multiplied by 2. And the last entry in the second row is obtained by multiplying the second row of matrix A by the second column of matrix C. Negative 1 by 5 plus 2 by 1 plus 1 by 0. And we perform the operations multiplication and addition to simplify the entries. 1 multiplied by 3 is 3 plus 0 plus 6. Or 3 plus 6 is 9. Next entry in the first column, negative 1 by 3 is negative 3. And 2 by negative 1 is negative 2. And 1 by 2 is 2. 2 minus 2 here is 0. Minus 3 is minus 3. Second column, we have 5. Product 0 plus 0 is 5. And the last entry in the second row, we have minus 1 by 5 is minus 5, plus 2, plus 0. Minus 5 plus 2 is minus 3, plus 0 is minus 3. And this is the product AC, a 2 by 2 matrix. Earlier we find the product CA, and the shape of the product CA is 3 by 3. Now we find the product AC, and the shape of the product AC is 2 by 2. Therefore, the product CA is not equal to the product AC because the two matrices CA and AC have different sizes. Lastly, we find the product BA. The shape of the product, the shape of matrix B is 3 by 3, and the shape of matrix A is 2 by 3. And you can see that the number of columns of B is not equal to the number of rows of A. Therefore, we cannot multiply the matrices B and A. Thus, you write, or we say that the product BA is not defined. Now, here in the product CA and the product AC, matrices A and C have different sizes, but they satisfy the condition for the product of two matrices to be defined. But if A and C are square matrices and their product is the same or equal, CA would be equal to AC. And we can conclude that multiplication of square matrices whose product are whose sizes are equal satisfies the commutative property. Again, for square matrices whose product are defined, they will satisfy the commutative property. But for matrices whose products are defined, like CA and AC, but A and C have different sizes or shapes, their products do not satisfy the commutative property. For your practice, please try the following exercises. For the following exercises, the given are the following. M is a 3 by 3 matrix with entries. In the first row, negative 1, 2, 0. In the second row, negative 1, 3, 1. In the last row, C, 0, 4, 1. N is a 3 by 2 matrix with 3 rows and 2 columns. Entries in the first column are 3, negative 1, 0. Entries in the second column are 2, 0, 1. P is a 2 by 3 matrix with entries in the first row 2, negative 3, 0. In the second row, negative 1, 3, 1. Number 1, find the product NP. Before you find these products, you check first if the product is defined or not defined by checking if the two matrices being multiplied satisfy the condition for the product of two matrices to be defined. In number 1, you find the product NP. In number 2, you multiply M by the product NP. And you already have the result. When you do number 2, you should already have the result for the product NP. And you check if the product NP can be multiplied by matrix M. Or you check if the product of matrix M and the product NP is defined. Number 3, find M to the power 2. Now, M to the power 2 can be written as M multiplied by M. So you write M squared as matrix M multiplied by itself. M multiplied by M. Number 4, find the product of PM and N. For number 4, you start first by getting the product of P multiplied by M. If the product PM is not defined, then the product PM multiplied by N is not defined. And number 5, find the product of matrices M and P. And that concludes our lesson for today on multiplication of matrices. In the next lesson, we will take up the properties of matrix multiplication. If you have question about the lesson today, you ask your question in the comments below. Thank you for joining me in my class in linear algebra today.